Okay, so let's look at some of the properties of materials that we can get from a stress-strain graph. So stress-strain, first of all, remember that stress relates to the force. Force per unit area, we can tell that because this symbol here looks like a piece of wire, cross-section of a piece of wire, and this one relates to extension, the strain. We can tell that because this looks like an E for extension. Okay, always make sure this doesn't look like an E, because obviously capital E is the gradient, the Young's modulus of its line. So I've got two materials. I have the red line, and let's go for three materials: red line, green line, and I hope it comes out okay on this. Let's go for an orange line. Well, what can we say about these lines? Well, I can say that the green line, first of all, is the strongest. This material is the strongest because it has the highest, the ultimate, if this is in tension, if this is tensile stress, the highest tensile stress. Okay, if this is compressive, then it has the highest compressive stress. But basically, the reason we know it's the strongest is because it goes the highest. This one down here is the weakest because it doesn't go as high. So we know it's the weakest, and the red one is somewhere in between. Let's get rid of that there for a moment. We don't need that. What else can I tell? Well, I can tell this one is also the stiffest. I can tell it's the stiffest because it's the steepest. Okay, the stiffness relates directly to the Young's modulus, or the Hooke's law. The spring constant. So it relates to the gradient of the graph. So I know this one is the stiffest. I know this one here, because it's the least stiff, is the most flexible. What else do I know? Well, I know that I can look at the area underneath. So I look at the gradient, I can look at the height of the line, the specific points. The one thing I haven't looked at the moment is the gradient. The area. The area under this line here is that kind of triangle there that's made by the pen going down here. The area under the orange line would be that triangle-y shape there, and the area under this line would be all of that underneath this red line to the green line there. So I can tell this one definitely has got the largest area, which makes it the toughest material. Toughness is a measure of how much energy it can absorb before it breaks. Looking at these two, looking at the orange line and the green line, it appears to be that they have similar toughness. Okay, so similar toughness as each other. Well, what do we know? We've already said about flexibility. This one here is more flexible than the stiffness. I'm just working my way through the presentation I gave you the other day. Let's look at elasticity and plasticity. Well, which one of these is the most elastic? Well, it's tricky to tell, but it appears to be, if this was a straight line, then this would suggest this was still within the limit of proportionality and still within the elastic limit. So this one here appears to be the most elastic, because it seems that it can stretch all the way to here and still return back to the original shape. This one's a little bit difficult to see sometimes from a graph, but that's certainly what it suggests, if this was a straight line. Which one's most plastic? Well, again, looking at this line here, the red line, it appears that this one is very plastic. There's a lot of plastic deformation there. I'd suggest that the limit of proportionality is probably about here, which means the elastic limit will be a little way after it. The yield point, so when the gradient begins to really shallow out, there's a big increase in strain for a small increase in stress, would be there, and then the failure point. We know after the limit of proportionality, after the elastic limit, everything is plastic. There's a lot of plastic deformation here. What we tend to get here, this tells us how far to the right it goes. Usually the further to the right they go, the more plastic they are. They can't continue elastically for that long. This one here is not elastic at all, which would actually make that, it's not plastic rather, at all. And it has little extension, little strain, which makes it quite brittle. So this one's tough and plastic. And because it's plastic, if this was under strain, then this would be, we could call this ductility. It would be ductile because it's able to be pulled apart, and it plastically forms when it's pulled apart. If this was compressive stress and it's squashed together, and that would mean, if there's lots of plastic deformation when it's squashed, that would mean it's malleable, the ability to be hammered into sheets. Okay, so let's say that this is under compression. I don't know if that's compressive strain, then this one would be malleable. as well. Hardness, well, hardness is a really tough one to get from this. However, most hard materials are not particularly plastic and malleable. They tend to be brittle and very strong and stiff because hardness is about how much it resists being scratched or indented. So this one would probably be the hardest, although you can't tell for definite from this graph. Okay, I think that's really all you can tell from this graph. If you were to name what material you thought these probably were, something that's strong, stiff, brittle, that sounds like a ceramic, maybe glass or china, something like that. Something that's quite weak but quite flexible, plastic maybe of some type, tough plastic, malleable, very malleable. This would probably be some sort of plastic, polythene, something like that. Maybe a soft metal. Although if it was lead, remember, lead is malleable but not ductile because it's too dense to hold its own weight when it's stretched into thin wires. I hope that makes sense.